All right. Thank you very much, Georg, for inviting me to this talk, and thank you very much for a kind introduction. And today, I'd like to join the very distinguished list of people that gave these seminars in the past. And I looked in the past seminars and saw that there were some mixed precision talks. But I think that this one is quite different from the other ones because I come to this from a strictly performance perspective. So I'd like to extract as much performance from these mixed precision algorithms as possible. And in a way, I look at the mathematics as a guide, but basically, I'm in the heart, I'm a performance guide. So let's first look around where this mixed precision came from, and it mostly comes from the hardware, and this is the kind of a overview of the landscape of the mixed precision hardware. And on the left, we see that there are a lot of startups that are basically getting either successfully, like Cerebras, keep releasing new hardware on the market that introduce new precisions that were not really present in the past CPUs and GPUs, and others are being slowly absorbed by larger players such as Intel. So that was the case with Habana here and Grok. On the right, we see the journey that NVIDIA made, and kind of makes sense right now to single out NVIDIA being the on the stock market in terms of the stock market value. It's the largest company, or one of the largest in the world. They started their journey very early, back in the Pascal era, and right now in Blackwell, as you can see, their precisions, it looks in the slide like they only have FP6, FP4. They're actually accumulating in the hardware all the precisions from the past. So in a sense, Blackwell will have the sum of all these different precisions. So the number of precisions seems to be growing, not decreasing. And another trend that we can observe is we have what we usually call the race to the bottom. So we're trying to have less and less bits and have whatever this hardware is used for. We're trying to use them with less precision, and the models that they run are adapted to use less and less floating point precision. Now, this slide, again, is just an overview. If you'd like to have a look and see much more detailed a survey of different hardware, and not just floating point, but also integer. So this is just like a very low quality reproduction on one of the slides of this very publication. So I'm leaving this here. Since you have a recording, you can look at look up this DOI, and it is freely available. And it's done by my colleagues from the MIT Lincoln Lab, and you can see that this landscape of hardware of different precision is much more complicated and comes in different forms, and we can look at it in terms of the performance, no longer floating point operations per second, because right now we also mixing in the integers, but also integer operations. So we just generically call it now giga operations per second, and the peak power. So it's important not to just have the good efficiency per second, but also have the overall power. So some of the accelerators you might have heard that Intel is planning to introduce a single card, accelerator card of 1.5 kilowatt consumption. It's just a card, so which breaks pretty much all the standards for server and cabling. So that's one side of the of the spectrum. The other side are really small deployments that we want to put in the field. So again, look at this survey. This is the DOI. You can see that the field of these new accelerators is very very vibrant. Now, the way we look at it, we kind of have this look right here. I put it in gray to kind of underpin. The HPC community is kind of seeing that we're kind of losing performance, not just performance per core, but also performance overall. The Moore's law is slowing down, and then there are arguments if it's dead already or not. So that's kind of reliving some comedy sketches. Are you dead yet? But the point is that the reason why we have this decline in overall performance is because we're squarely looking at the precisions that we introduced back in the 80s as a standard, and we kind of rely on them for our scientific codes. However, if we look at the color lines here, so these are the lines from the from OpenAI, and they basically show how fast they can compute. And so they call it petaflops days of worth of computing to train one of their critical or marquee AI and machine learning models. And they went all the way to 1960. So this is not a mistake. Right there, they actually included a 10 to the minus 12, something that was called a Rosenblatt perceptron. So the way I like to think about this colored graph, which is much different than the gray graph, is that the precision is basically diminishing all the way to the current 2020s. So back in the day, this Rosenblatt perceptron, he made it manually out of resistors, and he could regulate it and build the perceptron by manually adjusting the weights. And because it was analog, you can say that the precision of this little gizmo was infinite. So the machine learning community started with the infinite precision, and right now they are driving towards very few bits of precision that these models work on. And you can see that unlike our curve, this gray curve right here, is slowing down of performance per core, slowing down of the Moore's law. They're exponentials because, again, don't be fooled by the lines. This is the logarithmic scale, so the lines mean exponential growth in these petaflops per days that is required to train these models. So these lines are exponential, and then they actually change. So you can either say that the growth is super exponential, or the exponential rates basically increase as they train other models. So this is what's driving this this changes in hardware and also in algorithms. So let's take a look in more detail. What precisions we specifically are looking at. So FP64, kind of the bread and butter of scientific computing, is slowly being abandoned in all kinds of forms and fashion. And we're starting at FP32 as the reference point to measure the accuracy, and basically go down from that. And so I will show some experiments in these lower precisions, 16 bits. Both in the floating point and the integer, but also go down to this even lower precisions, int8 and FP8. And in FP8, it is very interesting that we see a splintering, and we actually, there is no one single precision that FP8 represents. Even the machine learning and AI community recognize that some of the time we need a little bit more precision, less meaning more mantissa and less exponent, and for some occasions the other way around. So they have for the weights, they usually want a lot of precision, so that's why they increase mantissa to 5 bits. And for the gradients that tend to be all over the place and be larger, they actually like to have exponent borrow a bit from the mantissa and move it into the exponent. And so we are very likely to have these kind of tricks being played more and more in this lower bit precisions that they were introduced in the Blackwell. We didn't see any hardware yet, but they were announced at GTC earlier this year. So we see that there are a lot of techniques that have to be used to make this precision useful. So there are some of them named here: aggressive quantization, scaling, and block-oriented formats. And I'll try to show how we in our numerical algorithms also try to use that as well to our advantage. So looking at the kind of at the hardware, how it's reflected and how the modern hardware is being shipped today. And this is just squarely looking at from the perspective of the precisions. You can see that this integer 22, both a floating point or integer, this is mostly done for graphics and gamings. So NVIDIA still ships the gaming units. And depending on which forum you go to, they might say that NVIDIA is the best gaming hardware in town. That's not the point. The point is that this piece of hardware is basically mostly devoted to the gaming industry and the gaming enthusiasts. And basically, this gaming cards, they have this area enlarged and others diminished. The machine learning and AI community gets these new tensor cores introduced in Volta first, and right now these tensor cores are now dominating the performance gains that these new hardware chips are getting. And the scientific community is now relegated to this very small margin of the chip, and so basically that is not changing. So that gray chart that I showed earlier, basically when the performance of FP64 is kind of relatively diminishing, that's basically because of this much less area of the of this chips being shipped is devoted to us and to our computation in higher precision. So we have to respond to this aggressively and shift towards using this piece of the hardware very judiciously and only when necessary. And in order to get performance gains, we have to look at other parts of the chip. And so this is the first time kind of I'm showing the more detailed summary of this precisions. So kind of to show you the consequences of lowering the precisions. So the one of them is the maximum value or the range of these numbers. You can see right here that for the half precision, something that is a fairly small number, 65,504, that's the largest representable number. So adding 1 to this creates an infinity. So in a way, 65,505 is already infinity in half precision. So in order to not overflow, we have to use other tricks, and I mentioned some of them in this talk. So that's the consequence. So BFloat kind of learned from this problem and said, no, we don't want such small numbers to be already infinity. So they kind of borrowed the exponent, 8 bits of exponent from the single precision. So they devoted 8 bits to it and kind of diminished the precision of the numbers. So the mantissa decreased by 3 bits, and it kind of created BFloat. And NVIDIA also has responded in a similar fashion, where they created this TensorFloat 32, which is the in a way the secretive floating point precision format that it's not really all that secret. Everybody knows about it, but the secret is that it's hidden deep in the hardware, and the hardware kind of has a freedom to judiciously translate into this internal storage all the other representations and compute in this intermediate storage, and then cast it as the results are coming out and are being represented in registers or in memory. So it has very formidable consequences for a lot of numerical analysts, and I'm sure that you heard their opinions about it in the past talks, that all of a sudden we lose all the guarantees that the standards, floating point standards, gave us, like IEEE 754 standard, that basically guarantees certain properties of these calculations. All these internal representations all of a sudden lose it. So there's important research going on in the reverse engineering what is really going on in hardware, and what we can really count on in terms of precision and accuracy and associativity and other properties of floating point arithmetic that we kind of learn to rely on. Moving on, measuring these things, again, I'm interested in performance. Measuring these things, it becomes more and more problematic. So I am part of the ML Commons, specifically scientific machine learning, where we try to measure these models and new hardware from the scientific perspective in more scientific units, for example, degrees of freedom per second or the particles per second. And there are other subgroups in ML Commons for doing HPC inference and training. So this is one way of doing the benchmarking. There are, of course, others. So I mentioned some of them by names. There are plenty others, hard to kind of, it's a dense field, and then newcomers come up almost constantly, because the field is again, with the super exponential growth, the field is moving quite fast. And so we're trying to adapt as well from the scale and HPC perspective. So we took the HPL, which kind of requires to use 64 bits for the benchmark. It does not stray into the other floating point formats. We try to create other derivatives, and I'll be talking about them: HPL MXP and HPG MXP. So HPL MXP just is a linear solver for dense problems, aggressively mixing precisions and introducing more complicated iterative refinement. And HPG MXP, it uses GMRES through and through and mixes precisions. And I will also talk about some work that went into creating this kind of benchmark. The iteration is at the heart of almost all of these algorithms that first try to do things in a lower precision and then make adjustments in a higher one, maybe switch to the lower one afterwards. Back in the 60s, when it was first introduced, by Jim Wilkinson in his one of his publications, it was almost mentioned in passing as saying like, oh, this is the procedure of solving systems of linear equations. And also, by the way, you can use this procedure to gain a few extra digits as long as you accumulate the residual in a very careful manner, potentially if you use it in higher precision. So this is this accumulation of the residual that Wilkinson meant. So as you can see, already there was some notion of mixing precision, but it was mostly looking into introducing judiciously higher precision into an algorithm that was just using 64 bits through and through. And the idea was that there is a potential to give the users even more bits of useful information that they would have gotten if they just used the working precision, which at that time basically was 64 bits. So we kind of broke up with this paradigm of increasing precision, and in 2006 we introduced this mixed precision technique. And so we were one of the reviewers back in the day said that like, this is nothing new. In the 60s, Wilkinson already did that. Okay, so in a way it was true, but Wilkinson kind of moved into the higher range of precision. We moved into the lower range. So this was the bold step here, was that we just decided to throw away the bits that the user gave us and operate on a limited number of bits for the sake of precision. So again, numerical analysts, strictly people that work on algorithms and try to extract accuracy, they will just shy away from it. We said like, no, that would be okay, and we gave exact conditions when this would work. And today, if you download LAPACK, not just today, but for many years since then, there is this new routine. So there are two letters. There usually is one letter in front of every routine. We had to introduce two. So there's D and S. D stands for double, S stands for single, and G is for general system solve. So this algorithm, this paper right here introduced this algorithm to the world, and now it's basically part of the almost every numerical library that tries to optimize and implement and provide LAPACK-like interface. That was back then, and the idea of performance, of course, is look carefully where the operations are being performed and at what rate, and basically judiciously lower the precision for those that are really high in intensity, and basically try to fix it up, just like Wilkinson did in this residual calculation. The problem, if we use 16 bits, is that our condition number has to be very low in order for it to work. So for 16 bits, and if we're looking at this large number that I mentioned before of 65,000, we have to have a condition number of the matrix to be less than 10 to the fifth. And if you've never heard of a condition number, or if you did, and you know that this kind of condition number is usually very hard to achieve in practice for many problems coming from scientists, yeah, that is true. So something else is needed, and I will show what kind of things can be used to remedy that. So in this paper, when we were just mixing the precisions, we just show these formulas. When we basically show that when we try to lower the precision, what we're doing, we're not solving the system AX equals B, but we're solving a system with an error. And the error is basically proportionate. It's just an additive error, because we're just taking a bits and just throwing them away. So that just it's like adding an error into the user input on purpose. But with certain assumptions, we can show how the conditioning of the matrix and other ways of basically being careful of accumulating the residual, if we can actually remedy that and deliver a fairly decent guarantees. And so that solver that I mentioned in LAPACK looks at the conditioning, looks at the iterations, and looks if the user problem is actually amenable to this. And if it isn't, the routine is safe. So LAPACK is always trying to be safe and give users a very decent answer. So what it does in the end, it switches to a fully double precision algorithm if the user problem is badly conditioned. So no worries in LAPACK. And this is generally a stationary method, and we will talk about how to improve it for even harder cases. So that's dense methods and kind of the old Wilkinson way of solving things. But if we look at the workhorse of almost all iterative methods, when the matrix A is potentially sparse or not even given explicitly, so basically we're looking at the explicit methods where basically, I don't know, physics or chemistry just holds the matrix in some sort of a data structure that cannot be extracted, but can give us, for example, application of that matrix to a vector. So it can give us a matrix vector multiply without forming the matrix explicitly. GMRes is kind of the workhorse. So we looked at that method and try to basically see how we can kind of squint and see where precisions could be applied. So kind of we decided that the outer part of the method should definitely deliver double precision to the user, so the user thinks that internally things are just as they used to be in 64 bits, but internally we're going to cheat, so to speak, and lower the precision and iterate. So kind of to simplify this whole GMRes algorithm, we can say that we did look at it as an inner-outer iteration. The inner iteration being GMRes in single precision, and outer iteration being GMRes in the double precision. And we're being very careful about accumulating the residual in double precision or even higher to make sure that basically the user sees a high quality solution, and that solution is and that solution differs almost very little from what would have happened if everything was done in double precision. So let's see if this works. So so that's even more simplified representation. So what we did is we decided to test it in practical cases. So not just doing performance, but also that make sure that we have the right answer. So these are different ways of doing the restart. So again, we have an inner outer iteration, and the question is where to invoke which. So we created a different schemes. One doing 100 inner iterations, 100 inner iteration, or basically stop the inner iterations when we reach the right residual, or basically first do some estimations, whether do one or the other, and then keep the iterations throughout the whole process. And we use the off-the-shelf hardware with NVIDIA Volta back in the day, and using Cocos, Kublas, and Sparse. And we use the standard CSR format. So basically, we didn't have a problem with the translating of the matrix formats. And so here is the example experiment, and this is set up in a way to not to give you an idea that it works universally and always gives you good results. So you can see that the one matrix right here, so the graphs here are going to show a speed up. And so the baseline is 1, meaning we get no speed up. Anything below 1, like this one matrix right here, is not a speed up, but a slowdown. And you can see it slows down substantially. So you can say if it fails really spectacularly. And the question would be, what kind of matrix caused such a failure? So you can see if you can zoom in on this a little bit, it says language. So this is not really a standard kind of a scientifically based matrix. It came from the science of language processing, which now we know uses a completely different methods, and not the sparse matrix methods. So in a way, it's an outlier. For all the other matrices coming from different fields of science, different finite element, finite volume analysis of different models, and some of them being potentially very badly conditioned, that we actually get speed up for some of them quite substantial, even more than mixing single and double precision would expect. For some of them, we actually get 4x, because the method and the precision kind of cooperate with the what is already embedded kind of in the matrix and the values in it. So on average, and this is the geometric mean of all the speed ups, we get about 22% speed up if we use modified Gram-Schmidt, and if we use the classical Gram-Schmidt applied twice, we get 65% improvement. Again, this is a geometric average, so we have this one kind of pulling us down and making the number much less than it really is. So without this one matrix, we could potentially get even higher speed up. So this was the speed up without a preconditioner. So again, this is all these results are performance oriented. In the back of your mind, you should keep this idea that we're trying to deliver the precision that is no different than what would have happened if we ran the whole thing in double precision. So applying a scalar Jacobi preconditioner into the mix, we can see that now we have a little bit more outliers. Some of the matrices really don't like this preconditioner. Again, the language matrix right here is still not cooperating, and our speed up drops. The mean geometric speed up drops accordingly. So we can try other preconditioners. You can see that we get a little bit worse results. So if we use ILU0 preconditioner, most matrices actually experience slowdown, and that is reflected in the mean. We get -7%, -4%. So things are not good. So maybe that preconditioner is just not good at all for this set of matrices. So adding ILU and kind of adding Jacobi solves, it fixes things. It fixes things for most of the matrices, and so we actually get a mean speed up of 8% and 14%, and so we try to recover. So as you can see, these kind of games of adjusting the preconditioners and matching the whatever we know about the physicality of the problem and how to precondition it correctly. Those games are have been played already, even if we just had one uniform precision for the entire algorithm, a double precision or single precision. So we're not doing anything different. But in addition, we're actually trying to take advantage of the fact that the lower precision will give us better performance, and we're using the same tool set of changing the preconditioners to adjust to the problem. So in a way, we show that nothing really changes. We just have one extra parameter to play with. What kind of precision we should use at different parts of the algorithm. So just to show the how this I've been talking about the precision and how we try to achieve whatever was possible with just using uniformly 64 bits. So this is the setup. Again, the same, so the precondition that I showed before, CSR format, the same set of software and hardware. And I'm just trying to do one matrix and kind of to show representative convergent curve for this matrix. And so we have on the left modified Gram-Schmidt for the orthogonalization. On the right, this classical Gram-Schmidt applied twice. And so you can see that the doing everything uniformly in double precision, we converge in about 200 iterations to a lower value. It turns out it's a stagnation point. We can actually go even lower at that. So the mixed precision going the orange one in between, it has an extra stagnation point as well, and eventually kind of reaches the same point, but requires about 3 times as many iterations. Again, these are iterations, so this is not necessarily time. And so kind of showing time and iterations universally on one chart is a little bit hard. So keep in mind that those iterations for mixed precision are a little bit less expensive. And this is just using single precision. We are stuck basically at the single precision, and we cannot move beyond that. So this is, again, these curves are known to the community, and just, again, we're just introducing another dimension that we can play these games with mixing precisions. Okay, so just to summarize this part, it is possible to play these different precision games with the iterative methods, such as GMRes. We definitely would like to move to even lower precisions for many parts of the algorithm, and I'm kind of going to show where this is possible. Kind of observing the TensorFloat in practice is hard because, again, this is internal representation, not really accessible to the user. And so other extensions include using flexible GMRes and be more aggressive with the mixed precisions. So flexible GMRes basically just was introduced because of the precondition not being constant, and the mixed precision does this to preconditioning. So these are all possible extensions, and there are many researchers that are looking at this very aggressively to exploit. Kind of moving on beyond the sparse methods and moving into the dense methods. So the HPL MXP benchmark originated from a mixed precision solver introduced some time ago, and it was meant to exploit these lower precisions in dense methods. And it was originally Aaron Carson and Nick Hayem that introduced this 3-precision iterative refinement when initially the dense matrix is factored in the L and U, and it basically then is being iterated on. And the speed up was very nice, 3 to 5, and it used a GMRes instead of a stationary method. And so the way it works, it uses multiple representations of the matrix, 64-bit, 32-bit, and 16 bits, different sizes, different conditioning. And so it carefully basically moving between these different precisions, there are different numerical tricks that were applied. So I've already shown that for the GMRes for sparse methods, here we basically say that our preconditioner is going to be LU factorization. The same LU factorization you get in LAPACK, you get in original HPL LINPACK, but it's going to be done in a very, in a sense, defective precision, very, very low precision that is very sensitive to conditioning. And in a sense, we expecting L to be well conditioned because it always has ones on the diagonals and less than ones below it. But U will potentially have zeros, so it represents a singular matrix. And according to the analysis of Carson and Hayem, it is okay to have such a defective LU factorization. And so they go into in their analysis how these defective L and U factors can still guide the this GMRes method towards the solution in a very effective manner. So if you can look at the talks by Leighton Hayem about this, it's very enlightening how defective numerical components of the factorization can still benefit the solver. So there are other tricks that have to be done. And so this is an example of scaling. If you look at the L and U factors, so I mentioned L is nice, ones on the diagonal, less than one below the diagonal. U can be all over the place. Again, it's a zero if it's a singular matrix, and this is really large values that can overflow. So we introduced some techniques in our prior work that basically allows us to spread this a growth of L and U factors evenly, and other techniques use basically splitting them between the different vectors and basically using tensor cores directly and kind of spreading different bits of precision between them to kind of increase overall quality and accumulate the residuals. Again, going back to Wilkinson's remarks, that the accumulation of this residual has to be in really high precision. So this is what happens in practice. If we use the unscaled values, we get basically no foothold, and basically we get, so these are digits of precision. So black just means no precision at all. In single precision, because we have nice exponent, we get nice convergence everywhere. But if we do all these techniques of scaling, we actually get a foothold into representable L and U factors. So again, that goes back to this idea of this L and U factors being less defective and guiding the GMRes method into its solution. So I mentioned GMRes versus FGMRes. As we get more aggressive with lower and lower precisions, we have to do flexible GMRes, which introduce extra storage and introduce a little bit extra computation, but allows the preconditioner to be truly non-constant and kind of change from iteration to iteration and allow more flexibility in terms of doing away with higher precisions. So how do we verify these methods? Generally speaking, it is hard. Sparse iterative methods are hard because they're self-correcting. I mean, that was observed even in the 1700s by Gauss, how these iterative methods were kind of self-healing and fixing things along the way, even if the people were making mistakes calculating it by hand back then. So we would try to basically do things numerically, rely on some properties and invariants that are still met in practice, looking at these L and U factors and reformulating or selectively doing dot products. And so in that way, it is actually still possible to verify them. And so this was actually scaled up to the level of Fugaku. So initial results in 2020 gave us 1.42 exaflops. Exaops, as we would call it. Again, it's in FP64 there was only possible to do half of that or even the third, and so right now Fugaku is rated at 2 exaflops and still at 400 petaflops in 64 bits, so 4.5 speed up. And so created a list based on that, and we're kind of publishing it year to year. You can see that the new machines are now appearing. So Fugaku used to be the top machine, but then other supercomputers join in. We now have Lumi from Europe, Frontier from Oak Ridge, And actually in the recent list, you can see that even the Argonne machine and Intel, that's actually what gave them the #1 entry at 10 exaflops, beating the machine at Oak Ridge. And in fact, this was the only way that they beat the machine for the ISC release of the top 500 at HPLM-XP list. So now we can look at these supercomputers in a very more rich way. So the black is the peak. It's basically the slowing down of Moore's law, is 64-bit precision, peak performance. Again, it's a peak, so it's not really that usable. So we turn it into something a little bit less contrived. So the Lin-Pack benchmark, again, it's not really a scientifically based anymore because scientific solvers don't use these kind of matrices, but at least something is calculated. There is some residual and precision achieved. So that's the red line. Down below, it's HPCG, which is the strictly a sparse solver and doing much less. You can see we're dropping 2 orders of magnitude in precision, again, because it's memory bound, but it's also using uniform precision. And the green line, green dots right here are the machines on top 500 that submitted this mixed precision HPLM-XP ranking. And so you can see that we can supersede the peak in double precision while delivering the same accuracy. So looking forward to the other things that are happening, this inference in the AI models happens in integers. Can we use integers in floating point algorithms, so to speak? Well, that's what we tried. So trying the range of different integers, range of small values, and kind of scaling it to bring it to the floating point and fractional values. So basically, we're looking at the 16-bit, 32-bit, and 64 bits. Again, they have no really accuracy because they don't represent anything, any fractions. So basically, we had to aggressively do a lot of scaling. We use a standard algorithm that you see in MATLAB, LAPACK, and other libraries, but we do aggressive scaling. So basically trying to move numbers into the range of -2 and 2 by pretending that the values that are represented are really scaled by an invisible scaling factor that we kind of hold to the side of the algorithm. And so we have to do different scaling for different parts of the matrix, different for L, different for U, and it works. So you can see that these curves kind of look almost the same, but now I'm telling you that these two upper ones are for floating point and the bottom ones are for integer. This is how the values, the errors in the values are across the matrix. So you can see that the represented values are roughly the same. And for most of the condition numbers, we get the same convergence curves for the residual, regardless of whether we do floating point or integer values. And so so these were the linear solvers, but important part that I worked on before is the eigenvalue solvers as well. So we're trying to compute the eigenvalues. Can we use the mixed precision? And so this technique that was pioneered by Bruno Lang and successive bandwidth reduction, we kind of reduced instead of doing successive bandwidth reduction, we said we're going to do the bandwidth reduction just in 2 steps. So we kind of we simplified Bruno Lang's formulation into the just 2 steps, and this is kind of the go-to method right now for the most eigenvalue problems. And we're trying to introduce mixed precision to it. And back in the 80s, this was this SICE algorithm that did this to eigenvalues that basically just perturbed the eigenvalues a little bit. And that's basically what we start to use. But we use it in a block fashion because, again, block fashion guarantees performance. So we're doing the correction that were done in the 80s, but in a block fashion. The problem, of course, that we're facing, that we're just having now this singularity at different scales of the precisions, and so we have to counteract that inside the algorithm. Again, not enough time to go into the details, and yeah, we do get a good performance. And we actually also have to iterate additionally for Newton-Schultz to keep the eigenvectors orthogonal. And the algorithm, however, gets a little bit more complicated. So there's this two-stage algorithm, and we stick in the iterative refinement for the eigenvalues around the other stages, and we utilize fully both CPU and the GPU. Does it work? It does, not for all the eigenvalues. So full disclosure, some eigenvalues will not converge as fast. Others converge just fine, just as if they were done in the in double precision. How well does it work in the in terms of speed up? So in real numbers, its speed up is less. In complex numbers, the speed up is much better. And so this is on Volta. You can see the 50% speed up on Volta for complex. However, if we move to the gaming card that has almost no support for double precision, our speed up all of a sudden jumps to 3.6x. Again, this is the card that was used as an example. If we can throw away double precision hardware altogether, we can do this and still compute very nice, accurate results. And it works, differently depending on how many eigenvectors we ask. So sometimes it's this blue and green lines overlap. So for this many eigenvectors, the method stops working. Again, it just depends on the gaming card. These values kind of are different. And this is the actual chart of timing. You can see that this mixed precision, there's an overlap of different stages, and this is how it looks in practice on the time chart. For the CPUs, it does not work at all. So the mixed precision is faster because there is only one machine. There's no GPU to kind of take the load off of the CPU. And so don't try this definitely on the CPU, but on the GPU. So this is an example on Volta. So the double precision is almost 10 seconds, and on mixed precision refinement, we lower it down to about 8.5. And of course, on the gaming card, the difference is it's much more stunning. Again, the 25 seconds for double precision goes down below 15 seconds for mixed precision. So this is my last slide. So this was a little bit of a whirlwind view of all these different things. I'm happy to take the questions, and thank you very much for your attention.
So one question I have is about eigenvalues. When you demonstrated that some eigenvalues don't converge as well, especially with sparse eigenvalue solvers, sometimes depending on the problem that you solve, you don't need the whole spectrum. You only need a part of the spectrum, or maybe only the lowest few eigenvalues. Of course, if I can get those, I will be fine. So is there any intuition about which eigenvalues do not converge as fast?
Generally speaking, it kind of depends on the iteration that we use in this particular method, because this is kind of a little bit similar to the Krylov subspace iteration. We kind of are at the mercy of what the Krylov subspace methods can deliver. And those methods usually look very favorably at the clustered eigenvalues. So you could say that the blue eigenvalues in this chart is one cluster of eigenvalues, and it basically, they all converge almost instantaneously. So that means that the Krylov method kind of took care of this cluster. Then they have this cyan, and then the yellow color. And then there are other clusters that are far away, and the method's basically trying to get to them, but basically it has to look through them, so to speak, through the perspective of these converged eigenvalues. So by far, I don't want to pretend to be an expert in eigenvalues. And so the people, as you said, that look for just the specific set of eigenvalues, those people perfected the methods that are able to zone in and kind of filter out, either by doing explicit shifting towards where they look for the eigenvalues, so they can actually make whatever they want blue, whatever they want cyan, whatever they want yellow, and whatever they want red, by doing this shifting, polynomial filtering. So I will let them decide how much they will use that, and this is kind of just a preliminary thing. But But generally speaking, this clustering of the eigenvalues, and for this particular case, it's the largest eigenvalues that are the most likely to converge fast, and they should be clustered nicely to even make it faster. But yeah, it's an excellent question, and it's an opening of a whole new field of basically eigenvalue problems with mixed precision.
Hello, so this is Uli. Hello, thanks for the nice talk. You focused mostly on timing, so runtime improvements. Another question would, of course, be, does it also save energy? Have you looked into that? Do you have results on that?
Yes. So measuring energy is usually fraught with with all kinds of assumptions. So on some of these, yes, we have energy. We have energy charts, and yes, energy is being saved a lot, because in addition to the fact that these tensor cores are fast, they're also energy efficient. And most of the greatest minds in designing silicon are basically now devoted to these lower precision units. So yes, energy is definitely saved. It's just that talking into, for example, when we make CPUs and GPUs, how do we account for the CPU energy if CPU is not being used? Do we count the idle energy and all that? So in that sense, there are a lot of assumptions. But yes, it's an excellent question, excellent point. Energy is definitely saved, and yes, we will, if for not anything else, doing it for energy is important.
Hi. Thanks for the nice talk. I have more of a library question. So let me first maybe specify the problem that I'm looking for, and I'm looking for a recommendation which library to, or which libraries to try out there in terms of mixed precision. So the main problem is a generalized eigenvalue problem of a dense matrix, which could get away with only calculating a set or a small number, or not a small number, but like a quarter of the lowest eigenvalues. So could you recommend, maybe in the view of mixed precision libraries, some libraries there that one could try out for this kind of problem?
Well, okay, so right off the presses, so there was a talk at the ISC this year in Hamburg that basically was talking about how NVIDIA did the chemical calculations, and I think that that's exactly what they were doing, generalized eigenvalue problem. And so they were calculating millions of eigenvalues per second, and so they are now putting it into both the single GPU Q-solver, and they're putting it into a multi-GPU Q-solver. So definitely, I would look into the program of ISC to 2024.
So maybe comment. Let me shortly comment on that. So Q-solver and Q-solver MP were already using for this purpose, but the lowest precision that I found in there is single. So I mean, it's kind of at least they can do single, but like in the spirit of like really mixed, like going down to half or even lower. Are there libraries around that are more or less ready to use?
Lower than single, I don't know of any. So trying to do that in lower precisions, I think it's getting harder and harder, because less and less of the calculations is suitable for that. So in that sense, it's I'm not surprised. It is hard to find. I've heard of some efforts to try to actually do the entire BLAS or even LAPAC. It's in not just lower precision, but in integer arithmetic, which uses basically the lowest possible in 8, which is very fast in these chips as well. So, but I think that's work that is about to appear in SC24 in Atlanta. So that's I think it's still unpublished work. So so you are on the bleeding edge. So you know, you might be actually the first one to publish some sort of a software about it. So so no, I unfortunately I don't know other than those examples.
There's a question in the chat. What is the target position for the mixed algorithm in the last slide?
The target precision is always double precision. So we're trying to have the computed residual and the error in orthogonality to be the same as it was for 64 bits. So so of course we cannot guarantee it for the single precision. So this is much lower. So we only run single precision for the speed to get the time, but we run mixed precision to get the same accuracy with some, of course, rounding error. Kind of, so there are some differences, but the order of magnitude, so the number of significant digits, should be roughly the same as it is for full double precision. Well, yes. So definitely, I agree with the sentiment that it is really hard because it's trying to retrofit an existing algorithm that enjoyed all these bits, and all of a sudden we're taking all those bits away. But definitely, it is necessary to aggressively not just remove the bits, but also change the algorithm. And kind of to point you in the right direction, there was an invited talk at the SIAM CSE, no, I'm sorry, SIAM PP meeting this year in Baltimore, Maryland in March, and there was an invited talk by the former Disney research researcher, and he was talking about exactly that when he took an existing multi-grid solver and by aggressively adjusting almost every representation, every calculation, doing block scaling, doing very careful quantization, he could do it in lower precision. His paper is on archive, and he gave an invited talk at the SIAM PP this year. So I don't know how to pronounce his name, but I can definitely send his coordinates and a pointer to the paper, when it kind of shows exactly that. You would not expect the multi-grid, multi-level solver to be amenable to that, but basically aggressively adjusting a lot of things, and some of them algorithmic, some of them scaling and quantization. It is possible. So yes, it will get harder, but it might be possible.